All right, so this last section is going to be on mutations that occur during protein synthesis. So here we're showing you a mutation. On the left is a wild type hemoglobin, and that's normal. On the right is sickle cell, and you can see that it is a collapsed. And it turns out that the mutant hemoglobin is a single change in one nucleotide. And this is called a point mutation. So going from the messenger RNA GAG to GUG actually changes a glucine to a valine. And by doing that, under certain conditions, hemoglobin will sickle. All right, again, this is a mutation, which is not very beneficial in kind of short-term thinking, because you can die from sickle cell anemia. It can make you very sick. But on the other hand, it actually is an advantage to have a light case of sickle cell to be actually heterozygous for the trait. We'll talk about that in genetics if you live in an area that has malaria, because it turns out that will fight people that have that are less susceptible to malaria. So, natural selection has chosen it for certain areas of the world. All right, so anyways, this is called a point mutation. This is where there's a single error, and what you're seeing is change in structure, which will also change in function. So I want to talk about these a little bit, and there are different types. There's a substitution. This is like what we just saw, that single substitution where one is changed. And we're going to have you do this in lab. There could be a silent change where the nucleotide is changed and this substitution causes no issues. Maybe it's like in the wobble where that last third one is changed, and by that means nothing happens. And then it could be a missense, which would be like the example of the hemoglobin, where you get a new amino acid. So instead of on the last one, instead of having glucine, you end up with valine, and that would be called a missense, mistake or mutation. And then there's also nonsense, whereas instead of it putting in a new amino acid, it now has it turn into a stop codon, which basically means that it's terminated. So if it happens at the very end of a strand, maybe it's not a huge deal and can still function, but often, mostly, if it happens anywhere in the middle or in the front, obviously, it can cause all kinds of havoc. You have a very small polypeptide instead of a large protein, and those are usually non-functional. And just to kind of give you an idea, if I asked you a question like, where would the worst type of mutation happen, we can talk about that in the Zoom session. All right, and the other type of mistakes is what we call a frame shift mutation. And these are insertions or deletions. So what you end up with these is you get a nucleotide either stuck in or taken out. Now the problem is we read things in the groups of threes, these triplets. The problem is that the way they're read is groups of three, and it's not like if you're reading a book and a letter's been lifted out and everything shifted, you're immediately going to see that there's something wrong. Something looks funky. These enzymes really don't have any way of doing that, so they just read the next group of three, and by doing that, everything can go to the side and can cause all kinds of major issues. And so we call these frame shift mutations. The whole thing, everything is read off either to the left or the right. These are typically more critical. Okay, and then again, I have the same slide twice, the nuclear pair, silent, missense, and nonsense. So make sure you know those. And I thought I went back. That's why. I'm thinking, why am I showing those again? All right, gene editing. You might have heard of CRISPR. It's talked about later in a chapter, but I think it fits here a little bit better. And so what CRISPR is actually a gene editing tool to actually read segments of DNA. Segments of prokaryotic DNA containing short repetitive base sequences. Each repetition is followed by short segments of spacer DNA from previous exposures to foreign DNA. So these bacteria have ways of reading when these things are what does not belong. It's a way for them to read, hey, this is from a virus, and they kind of remember what they were trying to put in. We are now using this CRISPR as a reading of our DNA. We are finding ways to actually take a target gene, something that we want in there, and to be able to use this CRISPR and actually go directly to a spot and place this in. So one of the problems before, we were always kind of trying to get these genes in place, and we had a lot of difficulty getting them where we wanted to be. CRISPR is actually allowing us to stick them exactly where we want them. Okay, and so this repetitive information. So we've taken this information from bacteria, and now we're using it. And I will tell you this: it is probably one of the biggest biological tools for use today, to allow us to edit genes in organisms. But I also tell you that it could be some of the scariest things, because although how do I put this? There seems like very few limitations on what we're going to be able to do. It becomes the ethical, what should we do? And with all our technologies, it always seems that especially legally, we're always behind. And already there's an argument on who actually designed this. It was who's got the trademark on it. Somebody down at, I believe it was UC Irvine, and then another group out of the country were fighting over who actually created this system. And so anyway, so it's going to be a great tool to get in there and target genes, especially if you have genes that are not functioning. But also it's, when should we use it? How should we use it? That is going to become a question in your time. So we'll stop there.